Hello everyone, we're group WR3A and for our project we were designing a waterfront robot. My name's Harjot.
My name's Liam.
I'm Utsav.
My name is Rahul. So the main requirements of this project included development of a leg structure with no continuously rotating joints and wheels. All the robot internals are supposed to be completely sealed from the elements. It is also important and necessary that the robot is self-powered and reliant using solar energy. The robot is supposed to be completely autonomous, but it also is supposed to have capability of being programmable by humans if necessary. Finally, the robot must accommodate garbage up to 100 centimeters cube and up to 1 kilograms. So based on the given requirements to us, this is the proposed design our group came up with. So as we can see in the slides, the overall approximate length of the robot is 667.1 millimeters. The approximate width is 860 millimeters, and the approximate height is about 407.6 millimeters.
Okay, so I was in charge of all the electronics for the project, and as a group, we decided it would be best if all the electronics were contained within one compartment, excluding the proximity sensors as they're on the sides of the robot. This choice was made for easy maintenance of the robot if anything were to go wrong. The electronic box is located in the middle of the chassis, and it's sealed when the garbage container designed by group WR3B mounts to the support risers shown in the current picture. Within this electronic box, we have the following electronics and their purposes. We have two DC motors where each motor powers a clan linkage mechanism. This way, the legs are able to spin in opposite directions, allowing for on-the-spot turning of the robot. There is also a camera facing forward, which relays live video to a software on board the robot, where it compares objects to a database of images. From here, it would send a signal to the garbage collection system from WR3B to scoop up the object or not. For computing power, we decided on a Raspberry Pi due to its open source availability and relatively low cost. It's also easily programmable by humans if necessary, which is a project requirement for our group. We have included a breadboard for wire interconnectivity, and here we also have a GPS module. This is necessary to locate the robot once it runs out of power and to empty it. Finally, given all the power draws and desired 8-hour operating period, the solar panel size needed is approximately 168 watts. Therefore, a 175 watt panel is used in conjunction with a battery to harvest extra energy, which can be stored and used once usable daylight is no longer.
So for the chassis design, we came up with a chassis which can be divided into two subframes, subframe A and B. Subframe A is basically just a lid on to close the subframe B. Subframe A provides mounting spots to mount supports for the solar panel. Two subframes are mounted together with 4 screws. Considering the project requirement, material selected for the chassis is aluminum 6061, which is strong, light, and rust-proof. The subframe B is manufactured in 3 different parts, and it's welded together. The mounting plate of the leg mechanism is welded onto the frame. Frame also provides mounts for sensors and cameras all around the chassis. All the electronics are placed in the center, in the electronics box in the center of the frame. The box has a lid on top of it, which can open up to 70 degrees. This is like the hood of a car. It allows the user to easily access the electronics if there is an issue with it. The garbage container can be placed on the lid using the holes in the electronic box and the lid. Chassis has a specific cutout to pass the wire from solar panel to the electronic box. There is a specific cutout for motors on the wall of electronic box to connect the motor shaft to the leg mechanism. The rubber seals have 2 conjugate parts, and each of the parts is mounted onto each subframe. And when the chassis is mounted together, the rubber seal fits onto each other, making the chassis waterproof. Flexible rubber bellows are mounted on the bottom of the chassis with each leg. The bellows are also mounted to the legs so that when the leg moves, the bellow moves along with the legs. The main aim for the bellow is to prevent the outside element such as water, dust, or sand to enter the chassis.
The design used for the locomotion system is based on an existing design called the clan linkage mechanism. The clan linkage mechanism is a forelinkage mechanism which converts rotational input speed to a linear output speed, which mimics the gait of animals. The legs are 25 centimeters in length, with 15 centimeters sticking out from the bottom of the robot. This length allows the robot to easily maneuver over various elevations as well as potential obstacles. The ends of the feet also have rounded and slightly pointy tips, which are purposely used to allow the robot to have better traction in sand. For our design, we went with 8 linkage mechanisms, with 4 facing the front and 4 in the back. The main reason for this was to ensure there are always legs touching the ground and to provide maximum stability for the robot. The linkages can be broken down into 2 assemblies, one on the right and one on the left. Both assemblies have their own gear reducers and contain 4 linkage mechanisms, with 2 facing the front and 2 facing the back. The main reason for this is to allow turning and rotation of the robot to be easier. To turn the robot towards the left, for example, the right assembly would move forwards and the left assembly would move backwards. This allows the robot to turn in a similar fashion to tanks. The gear reducer used for our design consists of helix gears, and the main reason for choosing helix gears instead of spur gears is that they have a significantly less vibration and are much smoother when meshing and will prevent any jerking motion in the legs. Both assemblies are mounted to mounting plates, which are a part of the chassis, and the linkages also mount to these mounting plates using pin joints. Pin joints are used because they allow the linkage to rotate freely and provide enough support to ensure the linkages don't fall apart. Here is a demonstration of what a robot with a similar design as ours making a turn. In this example, the robot is turning around a corner, and this is done successfully. And this is an animation of our robot. In this animation, we didn't include bellows because they were not able to move with the legs due to the way mating works in SolidWorks.
Now I will go over parameterization. Here we have a screenshot of the GUI interface. So the user provides the software with the gear train output speed they want. The user will also provide the software with the desired input shaft length. So the software then performs the gear and shaft analysis calculations to provide the user with an optimized face width and an optimized shaft diameter value, such that the safety factor is at least 2.5. The optimization code is also restricted to only allow for a shaft length of 6 centimeters to 15 centimeters. The range is selected because the mounting plate of the gears has a thickness of 10 millimeters and the face width of the gears ranges from 24.4 millimeters to 50.1 millimeters. So here we have 2 pictures from the parameterized SolidWorks assembly. The picture on the right shows the model after the user enters the maximum values allowed as input for the shaft diameter and the output speed, whereas the picture we see on the left shows the model after the user enters minimum values allowed as input for shaft diameter and output speed. So that was it for our presentation. Thank you everyone for listening, and any questions?